Hi, welcome to the Shiko Math Practice Lab, Learning Through Practicing. And we are in the unit Linearization. So this is the second practice about the topic linearizations. For our practice number 1, we did several problems. I think we did 8 or 7 problems. And we are doing kind of more mechanical type of the practice, right? So we just try to find how to find the differential, how to find the linearization approximation formula. And then in this practice, we're going to take a look at the word problems and where we're going to use the linearization type of the skill to solve some word problem. Okay, let's take a look at our problems here. We're going to practice 3 problems. And as always, we're going to start with the easiest one. Then we're gradually going to make the level is a little bit more complicated, but it's not too bad. All right. So first things here, okay, let's take a look. The first problem here, they say the radius of a circular disc is given as 24 centimeter with a maximum error in measuring of the 0.2 centimeters here. All right, so let's do a graph here. So this is a disc. And we say that the disk here, the radius we want is 24. But with the measurement error, that means that the gauge I'm using to measure it will have an error, and the maximum error is what? 0.2. That means I can measure this disk from the 23.8 to the 24.2, right? Because due to my gauge errors here, the maximum error, it's 0.2. So I could measure anywhere between here. I can measure 23.95 or 24.13, right? So now, because I know I have this maximum measurement errors here, I want to figure out what could be, if I use this gauge, I measure the radius, what could be the maximum error I find when I try to calculate the areas here. All right, so here, let's take a look. And then the number 2 is here. Let's try to see what we find. We want to looking for is A is equal to what? Pi r squares, right? All right, so then here the information, just like we see here, let's put this is number 2 steps, right? So that we say the maximum error is 0.02, right? So that means my dr, right? So could vary from what is 0.2, right? And I want to find what here, I want to find what is the error I could have for my areas here. Okay, so now let's try to take a look at the derivative. So I said the dA, take the derivative both sides, or you will say dA dr is equal to 2 pi r, right? Then you can just move the dr over. So this is 2 pi r times dr. Okay, so now I know here I can start to plug in the values here, right? So what is the, okay, so this one's here, the dr, like we said, the maximum error is 0.2. And the r is what? R is 24, right? So see here, now I have all my values here. So I know my area could be the 2 pi times 24 times 0.2. Okay, so I'm going to get a 9.6 pi centimeter cube here. So that means that the error for this area, the maximum error will be 9.6 pi centimeter square. So if there's no error, then what is your area here? Your area will just be the pi r squares, right? So your area, if it is no error, your area will be the pi r square. So pi r is what? R is 24. So it's the 24 squares here. All right. Okay. So that's the without arrow. So this is the maximum area you can have. That means the true area could be this one plus or minus 9.6. All right. Now the part B is they say what is the relative arrows. So the way we define the relative arrow is like we say, okay, so it's the arrow, the maximum arrow you're going to have, and compare to the true values here. If there's no, if there's, the no measurement arrows here. Okay, so now in here, the relative arrows here is 2 pi RDRs, right? Okay, so this is, we say this is a 2 pi RDR, and then the true area is a pi R square. So if you kind of cancel that and plug in the numbers, so this will be the 9.6 pi the 24 square. So you will get this is 1 point what? This is 1 over 60. So this is approximately 0.016. Then the percent arrows here is just you take the percentage, so it's 1.6%. All right, or the 1.6%, so it's or 1.7 if you're rounding that. Okay, so that is how do we define it, right? So the relative error is the possible error you're going to make, yeah, right? Your possible error going to make and compare to the the true values here. Okay, now this one is pretty simple. We love the circle, right? Because circle is very simple. The relation for a equal to pi r squared is kind of straightforward. Okay, now let's take a look at the second part here. The second part is that one side of the right triangle is to be 20 centimeters long, and the opposite angle of this side is measured is 30 here. So right, oops, what I did here. Okay, so the now in here, okay, so now we want to find with a possible arrow is plus and minus 1 degrees here. So I want to use a differential to estimate the maximum error. And what is the also want to find the percent error. All right, let's take a look at the problem number. So step number 1 here. Let's try to graph it. Right? So we have a right triangle. All right, let's put this is right triangles here. And here is the right triangle. Let's say the one side of the right triangle is 20. Okay, so let's say, okay, let's assume this is 20 centimeter. And the opposite angle is 30 degrees. Okay, so let's put here, this is my 30 degrees here. Okay, cool. All right, so then they say with the possible error of plus minus what? With plus minus 1 degrees. Okay, so if this is I call the theta, so let's see what are the things we know, what are the things we don't know here, right? So I know the d theta, they say the maximum error is a plus minus 1 degrees here. That means I can go 31 or 29 here, right? And then I want to find the what here, I want to find the hypotenuse. I want to find the maximum error you could have the hypotenuse. All right, so let's say here, this is x here. So I want to use a differential to estimate the maximum error of the hypotenuse. So that means dx, this is what we are trying to find. Correct? Okay. Now, after you do that, then also let's say the theta here is 30 degrees, right? Okay. Now, let's take a look at step number 3. This one is a little bit more complicated than the previous ones. The similar things we need to be careful is about the degrees to radians here, right? Okay, so now let's see here. Okay, so the first thing is let's try to put all this theta and x together. So this is my thetas, right? So this is the angles here. Okay, so I know, this is the x and the O. So I know the sine theta is the opposite over hypotenuse, correct? Well, that's cool. So now I can have x is equal to 20 sine theta, or if you like, you can say 20 cosecant thetas, right? Because we know the sine and the cosecant are the, the reciprocal of each other. Now the step number 4 is here. Let's try to take the derivative of both sides. So this is a dx, and this is a 20. So what is a cosecant? It's negative cosecant theta and cotangent theta. And don't forget the d thetas here. Okay, so as always, now the thetas here, right? So, okay, so we know the cosecant theta. So this is cosecant 30 degrees. And then here is a cotangent 30 degrees. Those are going to give you a value. So that's good. Then the d thetas here. All right, so the d thetas here we say is plus minus 1 degrees, right? But in here we cannot times degrees because then that's the units. So I need to change. So what is the C here? I want to change the 1 degrees. So I know the degrees and the radians change formula, right? So 1 degrees is pi over what? 180 radians, right? Okay, so it's 180 radians. So now I can start to change this one. Then I can do that because they said, so this will be the plus minus pi over 180. Now when I change it to the radius, I don't have units anymore. Okay, so what is the cosecant 30? So this is what? This is special angle, so it's 2. And the cotangent 30, this is square root of the 3 here. So now we said dx is equal to, so if you times the plus minus here, so it will be the plus minus, so it will be, so total it will be, so if you calculate, this will be the 2 square roots of the 3, the 9 pi. So this one will be plus or minus, means that's the error they're going to have, right? So if you plug a number that, so this will be 1.21 centimeter. Okay, so that means your real hypotenuse will be plus minus. So the real hypotenuse is what? Right, so here, so we know the maximum error when you measure is plus minus 1.21. So now they want to find the percentages, right? So I use the dx and the x. The dx I have, this is 1.21. So what is the x I'm going to have here? The x here, this will be what? This is the special angles, right? It's 30, 60, 90. So hypotenuse will be the double of the angle face 30. So what is the x here? So it's a 40, right? So I put a 40 here, and then I will get what are we going to have here? So we're going to have very close to 0.03. Okay, so we're going to very close to 0.03. So that means close to 3% errors here. That means if my measurement error has 1 degree differences, then my x going to offset like 3% of the true x values here, true hypotenuse values here. Okay, let's take a look at this one. This one is a little bit more complicated than the previous two, but also it's combined some very good ideas, right? So here, For the previous one, this is the highlight, right? We need to be very careful for these zetas here, right? We always need to change the radians because we cannot have a degrees, as our if you have a degree, you cannot do the operations like times, those things. Okay, now here, this is an interesting problem. So let's say, suppose the only information we have for a function is, wow, that's not very generous. So let's say the only information we have for a function, f1 equal to 5. And this is the derivative, okay? Be careful, this is a derivative, it's not a f of x functions here. And then we say, hey, let's try to use a linear approximation to estimate f09 and f1.1. Whoa, okay, so first things here, let's write down what we know here, right? So f of 1 equal to 5. This is a given, and we want to find f09. Okay, so remember the linear, let me write it again. So the linear approximation is Lx is f of a plus f prime a x minus a. So in here for this problem, I say, okay, that's good. So f1, so I can let the a is equal to 1. Okay, now I need to find f prime a. So how do I find f prime a? So f prime a, that means I want to find f prime 1. All right, so that's not bad. They give us this. This is 1, f prime 1. So what is here? This is a 2, right? So I know this one is a what? This is a 2 here. Okay, so now let's try to write the linear approximation. So I said Lx is equal to f of a is 5 plus f prime a is 2 and x minus 1. So this is my linear approximations, right? We did a lot of practice on our first video. Now they want to see estimate f09. That means I need to use this is f09. So I use L09 to estimate that. So this is 5 plus 2.9 minus 1. So this will be negative 1s, right? So it's 5 minus 0.2. So what is here? 4.8. Cool. All right. And then the next ones here, I'm going to use the 1.1s, right? Try to do the estimation. So 5 plus 2 times 1.1 minus 1. So this is 5.2. All right, so this is the first part is not very too difficult. Okay, so as long as you know how to read this graph, right? So here, this is the key part, right? So this is the key part. If you can figure that out, then your first part is done. Okay, let's take a look at the part B. I think the part B is very interesting. Let's say that, hey, you use the L.9 and L1.1, try to estimate those values. Are those estimator is too large or too small? This is larger than the true number? Whatever this true number is, I'm not sure, right? But this is a little too large or too small? Okay, so let's see here, right? So we did this before. So here, take a look. The f prime axis, right? So this is f prime axis here. And f prime x, this purple line is all what? Is positive, right? So this f prime x tell you f prime x is all positive, right? So all positive, right? So what's that mean? So let's take a look. We did this many, many times. We know that this is f prime x here. They are all positive. That means my f of x is increasing, right? But it is, okay, it is positive, but also f prime x is what? Is decreasing. Okay, so what that means, decreasing. So the f of a increasing and the f prime axis, right? So this is represent, okay, so be careful, this is represent the slope of the tangent lines, right? Okay, then we also see this is decreasing. So what's that apply to? That means that we still, because f prime still is the slope of the tangent lines here, but then we say but the tangent line become what? Becomes less steep, right? Because it's kind of like a, so I know my functions here, my f functions, my f of function possible. I always draw the picture that's not a, okay, so need to be careful when I draw this, right? So that means it's always need to be smooth, okay? So let me see if this is my f of x here. So if you take a look at the tangent lines here, right? So here, this is the tangent line, and here, this is the tangent line. As here is the tangent line. What's that tell you? See here, the tangent lines here become less and less steep, right? So, okay, so if it's less and less steep, that means the function has to be under, so the f of x has to be under the tangent lines here, right? So combine these two, so basically you see this information, that means the tangent line okay, so the tangent lines here, okay, so I'm get rid of that. Okay, so that means the tangent lines here lies what? Above the curve. F, right? Above the F curve. And also we know the tangent line is the linear approximation. So whatever we find the 4.8 and the 5.2. So for example, this is the 4.8, right? And the 5.2. So so what we see here is you see the slope of the tangent lines here. So those estimations, the red ones here is a linear approximation. Because of the tangent lines sit above the curve, right? So what are those estimators here? Those estimators are what? Are too large, right? So they are larger than the true f of x function. So that's why I said the part B, part A is not no, it's not too bad. It's not a big deal as long as you can find how to read the graph. But part B is a very good conceptual problems, right? So we tell you, the f prime x is all positive. That means fx has to be increasing. And also f prime x is like the start decreasing. That means, the tangent line become less and less steep. So if tangent line become less steep, that means tangent line has to be set above the curve. Then that means the tangent, this approximation, linear approximation, will be what? Will be overestimated. All right. Okay, that's it. That's the application for the linearization. And as you can find, it's very interesting. Okay. All right. It's nice to talk to you and hope you got, I hope that you practice the problem first and then come back here to verify the answer. And so make sure you understand how to do that. All right. Okay. It's nice to talk to you and have a good day. Okay. Bye.